So the purpose of the webinar today is just to give you a very basic understanding of what thermal shock test chambers are, where the test originated from, and how they're different from standard thermal cycling chambers. And again, we'll do our best to address any questions at the end of the webinar, so please feel free to submit those as we go along. Just a quick overview here of the presentation that we're going to cover. We'll first talk about where the thermal shock test came from and its origins, and then we'll talk about why it's important. And then we'll talk about the different kinds of specific thermal shock chambers that are able to be manufactured today. And then lastly, we'll finish up with talking about how they're different from standard temperature cycling chambers. So years ago, chambers weren't as advanced as they are today, and it didn't have the same kind of technology and efficiency as a modern test chamber would. However, customers and different manufacturers and even the military needed extremely fast transition rates, and there really wasn't a good way to do it in a standalone test chamber. So what they did is they moved samples by hand between two separate test chambers. One was kept at a constant hot temperature and one was kept at a constant cold temperature. So after a soaking period, they would physically move it from one chamber to the other, from hot to cold, and then after the cold soak, it would be from cold to hot. Now, this wasn't an extremely reliable or repeatable method of testing because one technician might take 30 seconds to move the test samples and another technician might take 45 seconds to move test samples. So it's varied in manual practice, but we've moved past that. And the mill standard that you see below is a pretty popular thermal shock test. And even though we've modernized the practices, it still calls out a specific time and reference to the original thermal shock test, assuming that you have two chambers instead of one modern test chamber. That's pretty much where the thermal shock test came from and how it started. And the reason why it's important is because the fast transitions will give rapid thermal expansion. And we'll just do a basic review of what that is. So let's say you have a cylinder of cold gas, and because it's cold, it's denser. It doesn't take up as much volume. When you heat that gas, it expands into a higher volume. And the difference between these two volumes dictates the coefficient of thermal expansion for a given solid, liquid, or gas, either in a linear surface or volumetric state. So why is this important? Well, let's take a circuit board, for example. Thermal shocks are very popular in the electronics industry, and this is just a picture I pulled off the internet. And just by looking at it, I see several different materials that are just on this individual board, let alone the components that the board would be attached to. So there's plastic in the microprocessor chip. The PCB would be made out of fiberglass, either tin or lead for the solder material, copper for the solder holes, and then aluminum, maybe even steel for some of the other smaller components. So because there's 5 or 6 or 7 or whatever the number is, different materials on this one circuit board, there's several different coefficients of thermal expansion that need to be balanced. So as the board heats up and expands, these materials are going to expand at different rates. And it all needs to be balanced so the board or individual components don't crack. Likewise, when the board gets cold, all the components are going to contract at different rates. So they all need to be balanced. And let's just take a modern analogy. And we'll just use a smartphone for simplistic purposes. At least here in Michigan, it gets pretty cold in the winter. So we heat up our cars and try to have a warm, comfortable drive into work. So let's say, for example, it's 75 or 85 degrees F in our car, and it's 0 degrees F outside the car in the snow in the winter. So you park your car and car's still running. You just check your email real quick before you walk into the office. That phone is exposed to 85-degree F air. And then as soon as you open the door to walk out into the cold before you get into the office, that phone is then exposed to 0 F air. That's a very small example of a thermal shock, but the same principle still holds. You're going from a warm environment to a cold environment in a very short amount of time. And the reason why thermal shock test chambers are used is because we can produce very extreme conditions, very, very hot, very, very cold, temperatures that consumer materials would never see in their normal operating lifetime. So if they can withstand a thermal shock test in one of our chambers, it can be pretty well sure that it's going to withstand the warranty period. So moving on from the original 2-chamber thermal shock test to more modern thermal shock test chambers, several different styles have been made to fit different customer requirements and needs. The first is a vertical style, and the picture you see is just from our shipping dock. And this transition is from air to air. So the red upper hot zone is hot air, and the blue colder lower zone is cold air. And we have a basket that products can be placed in, and it transitions from zone to zone at set periods of time. Vertical styles are really useful if you're pretty tight on footprint and you're using smaller and lighter test samples. It fits really well within the basket, and we remove the irregularity as far as transition's concerned. That basket's going to move the same time from zone to zone, from transition to transition, so it's very repeatable and reliable. However, if your products are really heavy or really large, we would recommend transitioning to a horizontal thermal shock. This way, we only have to worry about the rolling resistance of the basket compared to the whole weight of the product, like in a vertical up and down chamber. So in this instance, the cold zone is on the left and the hot zone is on the right. And underneath the windows, there are a couple service panels, and that's what houses the transfer mechanism. So the basket will transition from left to right to simulate, that hot and cold shock. Now, a 3-zone is a little bit more rare of a test chamber, but we still offer them. And this specific type of chamber is designed for those who are still following the original thermal shock test, where products would move from one zone to another in a manual fashion. So what this is, the cold zone on the left is in blue here, and that is fixed. It doesn't move. The entire hot zone, the right window you see, that whole zone moves independent of the basket. So it can move left to right. And when it moves right, it exposes the basket to ambient conditions. So it still holds true to that original thermal shock spec. But everything moves in a very reliable and time-precise method. So if you need 30 seconds, it'll transition in 30 seconds, and it'll sit there for 10 minutes or whatever your set points are. So some customers still use this, and we are able to supply that. So moving on, there are single duties, which we've talked about up until now, which means one basket. And now we have double duty. So now the basket is twice as big, and we've added an additional hot zone. And the reason why we add an additional hot zone instead of an additional cold zone is because it's more cost effective. So right now, the basket you see in the diagram is in the middle and the lower sections. And when it transitions, the cold middle will move to the hot top, and the hot bottom will move to the cold middle. So in this example here, the vertical style, you're getting twice as much testing for 50% more chamber. So if customers are concerned about product throughput, a double duty is a way to go. And double duty is also offered in a horizontal fashion. So we'll, instead of moving up and down, we'll move left and right. And this is again geared towards heavier products or larger products. And the double duty fashion will still provide increased throughput. So the 4 bullets that we've talked about so far are all air to air. The hot zone is conditioning hot air, the cold zone is conditioning cold air, and the basket moves between the two. There's a final specific thermal shock chamber that's called liquid to liquid. And in the image you see on the screen, that plexiglass door lifts up and that exposes the test space. And on the left-hand side, you have a cold bath, and on the right-hand side, you have a hot bath. And this test can be done with water, but it's typically not. Normally, we would use a Galden fluid, and it's a very expensive but very durable fluid where at negative 65 degrees Celsius, it's a liquid, and at 165 degrees Celsius, it's still a liquid. So it's for typically very light circuit boards. We're only limited to maybe 7 or 8 pounds for this specific chamber. But some customers are held to this kind of test for quality purposes. So if you do need this kind of chamber, we'll be able to help you out. So as you can imagine, because the construction of these chambers are very different from standard temperature cycling chambers, there are distinct differences in features that come with it. However, each feature does have its own limitation, and you can balance these features and limitations to make sure that you're going to get the chamber you need. Just because you like thermal shocks doesn't necessarily mean that's the best chamber for your application. So we just want to present these and make sure that you make the best decision possible. The first and probably most obvious feature is that you can get faster transitions on your temperatures. So you have one hot zone and one cold zone, and it's not just the air inside that's hot or cold. We're talking about the liner. The metal liner is all soaked out at the set point temperature. In the cold zone, all the coils are soaked out. So all the refrigeration or heating is devoted to transitioning the basket and your product as fast as possible. So that's how we're able to do that. The limitation on that is we need 2 zones, and especially with horizontal, it typically has a larger footprint compared to just a standard temperature cycling chamber. So something to consider. Again, when I was referencing, the coil is soaked out, we're able to use the refrigeration system to its maximum potential in just conditioning the product. So it's a very efficient use of the refrigeration and heating systems. But the limitation on that is we typically would not recommend that a larger thermal shock be air-cooled. Because that refrigeration system is running at full steam, we need a more reliable heat transfer method, and we typically wouldn't recommend air-cooled. We would recommend water-cooled for our condensers, just so the refrigeration system can run as efficiently as possible. So we have a transfer basket here, so that allows the specimen to move from zone to zone in a very repeatable and a very reliable fashion, and those don't come standard on temperature cycling chambers. The limitation on that is we require another utility. Our transfer baskets are typically air-powered, so we do need an air connection. This is normally not an issue on most industrial sites, but if you don't have air, that is just another consideration to make. And lastly, we can identify design issues quicker with thermal shocks compared to standard temperature cycling chambers. This is in line with the faster transitions on the first bullet, but just kind of looking through it with a different lens. Again, the fast transitions, if you think back to that circuit board picture, with all the different materials, all that are going to expand and contract at different rates, a thermal shock chamber will help find those issues faster. The limitation on that is thermal shock chambers will typically have a higher amp draw. For a standard temperature cycling chamber, you'll cool it, the refrigeration will turn off, then you'll heat it, the heaters will turn off, and you'll repeat. However, on a thermal shock chamber, the refrigeration system and the heating system are on at the same time. So again, this isn't normally a large concern on most customer sites, but if you're not prepared for the amp draw, that is something that will need to be discussed before purchasing a test chamber. So these were just the 4 main features and limitations that I could think of for this webinar, and they just point out that thermal shock chambers are very good for what they do, and we just want to make sure that if that is the test you need, that you're aware of all the considerations. So we're going to finish a little bit early here, but just to summarize, we just talked about the history of the thermal shock test and moving from one chamber to another because the technology wasn't as advanced. And then we talked about the importance of thermal expansion, and you can just think back to that circuit board picture. And then we talked about the development of thermal shock specific test chambers, and we talked about the different styles, the vertical, the horizontal, the double duty, and the liquid to liquid. And lastly, we just talked about how thermal shock chambers are different from standard thermal cycling chambers. So I'm just going to pause here for a couple minutes and give you a chance to write down that website and my contact information. Please feel free to reach out via phone or email with any questions in the future. Again, this webcast is being recorded, so you will be able to reference these slides for future use. And during that recording, you'll be able to click the links that are on the screen. And that's just our main website. We have a standard thermal shock brochure to help give you some more information. And then we have an informative video on one of our product series, so those should be pretty useful. So I'm going to check below to see if we have any questions, and please feel free to write down any of this information.
Yeah, Michael, this is Tim. We got a great turnout today, by the way, everybody. Thanks. And there's a couple questions on that a couple people put in. So if you want to address those, I also got a couple questions via email. So I can address those after you want to check on the 2 that are on the webinar. That'd be great. And then I'll go back to the ones that were emailed to me. Okay.
Yep. So I'm just going to go through the questions here. The first one. For double duty chambers, do you get double the output or is it 50% more? Yeah, that's a good question. It's really just how do you look at it? Normally there's only 2 zones, a hot and a cold, and then we add a 3rd zone. So that could be interpreted as 50% more zones because we're going from 2 to 3. However, the basket size doubles. So that's where the name comes from, and really it's just how you interpret it. The next question here, what other parameters such as expansion are studied? How is data being acquired? So thermal expansion is the main area of concern for thermal shock chambers. However, the others are just if the device can operate at extreme highs and extreme lows. So that's another area of study. And inside the test chamber, there is a traveling port. So as the basket moves up or down or left and right, the port moves with it. We can't put a port in the door or the sidewall because the basket moves, but the port allows for thermocouples or other temperature monitoring devices to capture the data. So that can be recorded, and then we also have sensors on our supply air of both the hot and the cold zone. So you can combine all of that data together to make sure that the test is meeting your requirements. Okay, another question here. How do these multi-chamber systems compare to single-chamber thermal cycling chambers? What are the key pros and cons for multi-chamber versus single-chamber thermal testing? So for that, I would just ask when the a recording is sent out, you just look at the key differences and features and limitations. I tried to cover the main ones there. Another couple just key differences is with the thermal shock chambers, you're going to have faster transitions. With standard temperature cycling chambers, generally speaking, you'll have slower transitions. So there are other pros and cons that go along with that, and I just ask that you look at that slide again. So with Halt-Haas testing, the question is, how does this compare to Halt-Haas testing? One, the thermal shock chamber is just for temperature, hot and cold, and the whole test area is being conditioned. So while the zones are soaked out, the refrigeration and heating systems are directed to heat the product as quickly as possible. With Halt-Haas, there is a vibration element that can be introduced, and typically Halt-Haas will also utilize liquid nitrogen. That will give upwards of 70 C per minute change rates on the product, and typically thermal shock testing won't be that high. So the main differences would be thermal shock chambers don't have vibration, Halt-Haas will. Thermal shock chambers are faster in transitions when compared to standard temperature cycling chambers, but not as fast as Halt-Haas. Another question here. Is Weiss Technik only offering customized equipment, or do you have equipment on stock that can be delivered immediately? Yes, the couple of pictures we showed were some of our custom units, but we do have two different thermal shock models that are in stock and can be, delivered at customer request. So if you do need a stocked unit, when you reach out to us, just please let us know and we'll direct you to one of those two models. Is the Weiss, and the last question I have here, is the Weiss Technik product offering, does it have special benefits such as lower energy consumption? And the answer is yes. We have special software in our controller that has been optimized for thermal shock specific use. So one example is our energy savings mode. So when the basket is in the hot zone, it will turn off the refrigeration system and it will only kick back on before transfer. Likewise, when the basket is in the cold zone, the heaters will be turned off and will only turn back on prior to transfer. We've seen that this can save customers upwards of 40% on their energy consumption, and that is unique to Weiss Technik. And Tim, that was all the questions I have here.
Yeah.
If you had any more, I can address those.
Yeah, I got a couple via email, so great questions. Very active group today. We love it. So the question here is, Michael, is what is the weight limit when you would change from a vertical style to a horizontal style thermal shock? So a good question. I know we talked about this before, but if you want to address that, that'd be great.
Sure. For our in-stock models, we have a 55-pound and 110-pound weight rating. And for our custom units, we have a 125-pound weight rating. If it's higher than that, we'll probably recommend that you transition to a horizontal style, or there's the potential to upgrade the transfer system to account for that larger weight. But just for a rule of thumb, the 125 pounds would be your go-to number.
Okay, great. Another one came through here via email is, what do you do differently if lithium-ion batteries are the test sample? So something to do with battery testing. Another great question.
Yes. So for lithium-ion battery testing, the same safeties that you would see in a standard temperature cycling chamber would also go in the thermal shock chamber, but the difference is we would have two sets, one for the cold zone and one for the hot zone. That way, regardless of the basket position, your product will be accurately monitored and safety will be properly accounted for.
Excellent. And just one last one, can you explain the traveling port again? I know you mentioned that in one of your slides, and there's a question, explain that traveling port, Michael.
Yes. So with the thermal shock chamber, we can't put ports in the windows, the doors, or anything like that because the basket moves from zone to zone. So instead, we have a port that's connected to the basket that leads to the outside of the test chamber, and you can use that traveling port to introduce your thermocouples or other temperature monitoring devices.